So let's thank again Tadashi for this nice talk, and we invite the next speaker.
Thank you very much.
Krishnan, are you there?
Yeah. Hi, Sudhakar.
Yeah, please try to share your screen.
Yes. Can you see this?
Yeah.
Okay, so shall I begin?
So the next talk is by Narayan from CMI, and he'll be talking about cosmologies, singularities, and quantum extremal surfaces. It's almost 5 o'clock, so 5:20 up to 5:25 you can go ahead. Around 5:20 I will give you a signal.
Sure, thanks. So it's a pleasure to be here, and I'd like to thank Alok and the organizers for this this nice conference and the invitation to speak. It would be great to be in Roorkee, but this is pretty good also. Am I audible, by the way, just to check?
Yeah. Sorry.
Okay. So I'm going to talk about aspects of cosmology, singularities, and quantum extremal surfaces. This is based on these two papers and a collection of people. 𝗤𝗵𝗶𝗿 and Partha are postdocs at CMI. Manu was a student at CMI. Hitesh and Kaveri are currently beginning students at CMI. So I'll talk about certain aspects of ADS cosmologies and classical RT-HRT surfaces to begin with, and then I'll talk about quantum extremal surfaces, towards which I'll talk about two-dimensional formulations of these theories. And in the last part, I'll talk about null-Kastner singularities and quantum extremal surfaces, and if time permits, towards the end, I'll talk about certain aspects of digital. So it's nearly 25 years since ADS-CFT began, and it's still quite interesting and important to understand time-dependent phenomena in string theory and holography. There have, of course, been various studies over the last many years. So I'm going to focus on trying to ask questions about Big Bang or Big Crunch singularities, where curvatures and tidal forces diverge, and so you would expect that GR and general relativity and notions of space-time geometry break down. The hope might be that holographic or some stringy description provides a UV completion and marches on. Okay, so in the last several years, we've seen entanglement as a very insightful holographic probe, specifically in terms of classical RT-HRT surfaces and quantum extremal surface probes in more recent times. Okay, so so this is going to be the theme of this talk on studying aspects of these sorts of extremal surfaces and these kinds of cosmologies with singularities. But before going there, maybe it's useful to have a prelude for singularities and string theory at a very broad brush level. So of course, we know that there's a long history of studying singularities and their resolution in string theory. So for orbifolds, for example, just conical singularities, spatial conical singularities, we know that these are singular for point particles, but strings have extra light winding modes. Okay, and these provide resolution modes of the singularity. This is well known. Null singularities are essentially singularities in time, but in light cone time. We have examples like singular plane waves or null Kastner singularities, which are equivalent. And it's again known that strings can be quantized explicitly in these kinds of backgrounds. And what's been known is that strings become highly excited in the vicinity of the singularity. Space-like Big Bang or Big Crunch singularities are somewhat unclear, it's fair to say. So there are again several toy models, well, not too many, but several toy models of holographic cosmologies with Big Bang or Big Crunch singularities, and some of them I'll talk about. So the bulk gravitational description breaks down, and you might ask questions about whether the dual field theory provides the right variables to go past and to march on. I won't have much to say concretely on this question, but it's probably a good idea to keep this broad question in mind about what are resolvable singularities in string theory and holography. Okay. So with this prelude, let me just go on to talk about old work actually on ADS cosmologies and duals, and then more recent work where we studied classical extremal surfaces. So here is a prototypical example. So this is the isotropic ADS5 Kastner space. It's basically a space where this Kastner space-time has been embedded in a particular way. And you can see that at t equal to 0, there's a space-like Big Crunch singularity. If you look in terms of the dual dual theory, you can see that the gauge coupling goes like e to the psi, which actually goes to 0 as t goes to 0. So you might ask whether this is actually given example suggesting a weakly coupled CFT at the location of the singularity. And if that were true, then that would provide a way to continue past. Okay. In detail, it turns out in a series of in a body of work with Sumit Das and Sandeep Trivedi and Adilawad and Jeremy Michelson, Suresh Nampuri long back, what we ended up finding was that a weak coupling analysis, if this were true, you could ask questions about a weak coupling analysis of the dual field theory, and this suggests that this actually shows that interactions are in fact important, and the gauge theory response ends up appearing singular. Null singularities appear better. Null singularities, by null singularities, I mean that the gauge coupling is a function of light cone time. These appear better in the sense that the kinds of problems that happen here do not happen in these kinds of cases because the special properties of these null of these light-like variables. In this case, weak coupling appears consistent. Now, there's a long song and dance here. I'm not going to go into that. But in hindsight, it's perhaps fair to say that generic severe time-dependent deformations on the vacuum state are expected to thermalize on long time scales. In other words, they might be dual to black hole formation in the bulk. So this perhaps suggests that if you want to construct a big crunch, then perhaps you should have something non-generic. So this suggests that perhaps non-generic initial conditions are required for a big crunch, which suggests that the dual CFT state is perhaps non-trivial. Okay. Now there have been further various interesting insights that were uncovered by Engelhardt, Horowitz, Hertog, and various other groups over the years. I won't have much more to say about this. I'm going to put a new spin on this whole thing. New angles on this collection of questions, but these questions I think are important and remain, and it would be nice to understand if this sort of intuition and expectation bears true, and if so, what might be ways to understand big crunch singularities in string theory and holography. If there are any quick questions on this, on just this broad background, it might be good to take them right now. If not, I'll carry on.
Please go ahead.
Yeah. Okay. So in more recent times, we've been seeing over the last actually many years, we've seen that entanglement provides very useful holographic probes. And in the current context, I'd like to explore the behavior of high-dimensional extremal surfaces with regard to the big crunch singularity. So in particular, the ADS-Kastner space. So there's a long collection of things that one can do, and one can do it in great detail. And what we end up finding is the following. So firstly, it makes sense to study strip-shaped subsystems in these cases. These are codimension 2 classical RT-HRT surfaces. They're parameterized by these sorts of by 2 functions of this kind, basically. The time dependence basically means that the surface dips into the time direction also besides the radial direction. Okay, and here is the kind of picture that we end up finding. So just to give you a sense of what this is like, let me just zoom into this. What did I just do? So this is the kind of picture that we find. Here is a boundary theory. Here's a boundary space. The singularity is way over here, far above. This is at t equal to 0. Everything I'm thinking of is in terms of a big crunch. Here is the anchoring time slice. So what do we usually do in studying such extremal surfaces? We study surfaces of this kind. We look at boundary subregions of this kind, and if this were a time independent space, here is a constant time slice, and the surface would then lie on this constant time slice. But in this case, there is time dependence in the background, and this time dependence basically forces the extremal surface to bend in the time direction also. Okay, so in particular, an extremal in this case, it's possible to do an explicit analysis of this of the system, and what we find is, why is this not moving? Sorry, yeah. So in the semi-classical region, far from the singularity, it turns out that studying this extremization process is quite reliable, and you can study this in great detail. And what we find is that the surface lies almost on a constant time slice. In other words, there's mild time dependence, but it bends away from the singularity. Okay, so the surface looks like this basically. Okay, so there's mild time dependence and it bends away. So the singularity is somewhere here, and the surface basically bends away. So in some ways, the singularity region appears repulsive in some ways. Okay. So with this in mind, it's interesting to ask, what do quantum extremal surfaces behave like, and whether we and can we get some insight into how these behave in the vicinity of the singularity, and can we probe the singularity region through these sorts of quantum extremal surfaces. In order to study these quantum extremal surfaces, I'm going to take a digression into studying just two-dimensional gravity models and cosmologies. So the last many years, we've seen that there have been various studies of nearly ADS to holography. We know that extremal black holes and black brains in the near horizon throat regions give an ADS2 cross a transverse space type space-time. If you compactify this transverse space in the IR limit, what you end up with in the IR region, what you end up with is JT gravity plus matter. The action of JT gravity looks like this. Okay. You could ask what happens for more general two-dimensional gravity theories. These can also be shown to arise as two-dimensional subsectors of higher-dimensional gravity on spaces like that. Okay. So if you again compactify this transverse space, what you end up with is a generic two-dimensional theory of this kind. Okay. Now the phi here is basically the two-dimensional dilaton, and it basically corresponds to the higher-dimensional transverse area. The U of phi is a general dilaton potential. Okay. Now, if U were equal to -2 phi, what you'll end up with is JT gravity, but otherwise you end up with something more general. The kind of reduction ansatz that's at play here is something like this, and this is the two-dimensional space that we are talking about. In addition to compactification on this transverse space, we also carry out a Weyl transformation to absorb the dilaton kinetic terms into the curvature. So this is standard convention in this literature, and that's all I'm employing here. Now there is a sense in which some sort of effective holography is at play here, in the sense that we are focusing on a subset of bulk observables and their duals. We're only focusing on this two-dimensional subsector, and these sorts of generic two-dimensional. If you analyze this in some more detail by looking at specific observables, for example, the suggestion that comes out is that such generic two-dimensional theories are akin to higher dimensional gravity. So they're not near JT, so to speak. So for example, if one looks at the reduction of higher dimensional ADS, for example, what you end up with is a dilaton potential that looks like this. And you can then study observables like the holographic energy momentum tensor or correlation functions and so on. And these reflect the higher dimensional theory. So this we can turn around, and then we can say that this, we can use this to say that we can use a two-dimensional theory as a diagnostic of the higher dimensional theory. Okay. Now this is only an approximation, the two-dimensional approximation to a fuller theory, and so you might ask that this is just an approximation. It is an approximation, but it turns out to be adequate for some aspects, including entanglement of the kind that I will talk about. Okay. So the kinds of things that one would like to do if one wants to use these two-dimensional dilaton gravity models as interesting playgrounds for a big crunch or a big bang are more complicated. So one technical route that one can take is to look at higher dimensional cosmologies and then do a dimensional reduction to 2 dimensions on the transverse space in this way. So that again specializes to only certain classes of such cosmologies that one can address, but that is still a sufficiently broad class, it turns out. And it turns out that the minimal class of theories that allow such interesting playgrounds is theories of this kind. So this is a two-dimensional dilaton gravity model with a dilaton potential that couples the two-dimensional dilaton and an extra scalar. This extra scalar you can think of in certain cases as the analog of the string coupling as a dilaton in higher dimensions. So what we would ordinarily call the string coupling in higher dimensions. So this extra scalar leads to non-trivial dynamics. The dilaton coupling here arises from this reduction of the minimal scalar action in higher dimensions. Okay. Now, this is a more complicated theory, and but it can be used for the kinds of things that I'm going to tell you about. So the equations of motion are in detail something like this, and we can cut them down to size. We can actually solve them in great detail, it turns out. But first, there's a simple observation that comes out right away. If one looks near the big trans singularity, one can show that that there is a universal subsector that seems to emerge. Okay, the universal subsector is something like this. The time dependence of the dilaton and the metric and this extra scalar turns out to be pinned down to be something like this. Okay, this is, you can see this by looking at these equations, the equations of motion, and looking in the vicinity of what you might think is a singularity, and then expecting that the time derivatives are going to be the dominant terms, and then focusing on those. Then you end up with a subset of equations of this kind, and now you can see that the dilaton potential and all asymptotic data has disappeared, and you end up with this universal behavior. Of course, it's universal in the sense that there is a universal form of this kind, but this relation, for example, is between these exponents is something that that is still general. I mean, sort of pins down these exponents, the relation between the exponents, but doesn't pin down the exponents completely. Now, one can do more. One can look at these equations and put in a scaling ansatz of this kind, and then actually just solve the equations. If you stick in a scaling ansatz of this kind, then the equations of motion become basically algebraic equations for these exponents. So given these two-dimensional fields, a higher dimensional cosmology looks like this. Okay. So if you take this sort of scaling ansatz for these two-dimensional fields, what you find, you can of course find the known cosmological solutions that have been known before. So for example, one can show that the isotropic ADS Kastner that I was talking about earlier comes out as one of the solutions. Its two-dimensional form looks like this. Okay, so in the two-dimensional, in terms of the two-dimensional background, this ADS5 Kastner, this ADS D+2 Kastner looks like this. Okay, so it has this form. I'm suppressing certain scales here. Well, in particular the Kastner scale, which will play a role at some point. The R here, the capital R here, is the ADS scale that was there in the higher dimensional space. The dilaton, you can see, has this universal behavior that I was saying earlier. And these exponents, you can see, are in fact related in the way I was saying earlier. Okay, but there's also various other families of such cosmological solutions that exist that we found using this two-dimensional formulation that I think were not known before. So these include more non-trivial cosmologies with non-relativistic asymptotics, hyperscaling violating Lifshitz cosmologies, and so on. I won't have much more to say about them, but it's interesting to see that they also exist and they can be found in this way. Now, armed with this two-dimensional formulation of these cosmologies, we'd like to understand what quantum extremal surfaces behave like. So before I go on, any quick questions? This might be good to take. Okay.
Narayan, these solutions you found here in this particular case, are they stable solutions?
Stable meaning?
If I perturb around these solutions, and will they affect the results?
Well, these are not supersymmetric or stable in that sense, if that's what you're asking. They are cosmologies, and that's all that they are. You could ask a question about whether the two-dimensional approximation is good enough and so on, and it would not be good enough if we find that we are hitting the near singularity region in some way. But it turns out that as you'll see, the two-dimensional approximation ends up being consistent, and you'll for many cases, as you'll see.
Thank you. Let's go ahead.
So there have been exciting recent developments in the black hole information paradox, as we've seen over the last few years. There have been new insights from the generalized entropy and quantum extremal surfaces. We've seen two-dimensional CFT techniques that can be used to adapt the Calabrese-Riccardi formula for the subleading bulk matter contribution to the entanglement entropy. So in particular, the generalized entropy looks like this, and this is the kind of expression I'm going to focus on, and I'm going to say more about this soon. This is the classical area term, and the bulk entropy is this. I'll have more to say about this very soon. One might ask if one can study, if one can gain any insight into Big Bang or Big Crunch singularities from these sorts of tools and ideas that we've seen in the black hole context. Now, at first sight, you might think we expect large linear quantum gravity effects here, and so semi-classical approximations will break down. So do we expect to gain anything? Perhaps studying simple toy models and quantum extremal surfaces as probes will give insight into cosmological singularities, and this is what we end up finding. So we do end up learning some things from these studies. In everything I'm going to say, we'll be mostly studying closed universes. So there are not going to be horizons, and so there's no appreciable entropy. So it's quite unlike the black hole case in that sense. We'll end up taking bulk matter to be in the ground state, which is, you would think, reasonable, far from the singularity. It's then also consistent to say that there's no entanglement with elsewhere. In other words, auxiliary universes that could be regarded as purifying universes for if we were talking about mixed states. Okay, so there are a few more points that come about in this formulation and in the way I'm using them. So here is the generalized entropy. This is the bulk entropy with the curved space effects put in as Almairi and others formulated it. We'd like to, so this delta squared here is a space-time interval between the observer and the quantum extremal surface. The quantum extremal surface is going to be taken at the space-time location r, t, and the observer we're going to focus on is a holographic boundary observer at t0, 0. So the observer is on the boundary at r equal to 0, and it's had a time coordinate t0. So firstly, this generalized entropy pertains to the two-dimensional theory that arises from the dimensional reduction of this high-dimensional space in this formulation. All the subsystems here are necessarily the full space because we've compactified the high-dimensional transfer space. So the quantum extremal surface now is a point in the two-dimensional space, and so this looks like it's the IR limit of the high-dimensional RT surface that I was talking about earlier. We'll take the two-dimensional matter to be approximated as a CFT in the ground state, and you might think this is reasonable, far from the singularity. We'll also impose this condition that the central charge of this matter lies between 1 and 1 over g. This basically says that the classical area term is dominant, but S bulk, the bulk entropy term, is appreciable. Now, if the S bulk, if the bulk entropy term overpowers S classical, the classical area, then the Bekenstein bound will be violated, and this might lead to the phenomenon that's been called islands in the formulation of Hartmann and company. Okay. So
5 more minutes.
Yeah, sure. So it's useful to focus on a time-independent example just to get a sense of how this works. So I'm going to just focus on this ADS di+2 reduction that I was talking about earlier. The two-dimensional background then is just this. There's no time dependence here, and so the generalized entropy is basically a function of one variable. It's the function of just this variable, the radial coordinate. If you extremize with this, then you can see from this expression here that both these terms, right? Both these terms are negative. They come with the same sign. And so if C is positive and DI is greater than 1, you can see that there's that the only solution here is R star goes to infinity. Both these terms independently have to vanish. This means we end up with the entire Poincare wedge. Okay. So here's a picture of this kind. So this is the boundary, and we end up with this. We end up with R star going to all the way to the to infinity. So you get the entire Poincare wedge. This is what you would call the usual entanglement wedge for ADS2. Okay. And if you analyze this more, you can see that the on-shell entropy, in fact, essentially is vanishingly small. And this is consistent with the fact that this is the ADS ground state. Now, you can recast, it turns out, this expression for the generalized entropy in this form. So you can always recast it as phi plus essentially some constant times log phi. And so you can see that in this case, as long as phi is not too small, the S bulk term is always subleading to the classical area term. And so the Bekenstein bound is not violated, and there are no islands. Now, had we appended a region, a flat non-gravitating Barth region, as is important for black hole studies beyond this radius boundary, then you would have a modification of this expression, and that turns out to lead to islands. Okay, but that's not going to be physically relevant here because we're talking about closed universes, and it's consistent to talk about this as a universe in itself. So with this intuition, where we can see that for these sorts of cases, we end up with the entire Poincare wedge over here. We look at these cosmologies. So I'm going to look at this ADS D plus 2 Kastner reduction, and the two-dimensional space then looks like this. The two-dimensional background looks like this. You might think that the observer, at least if you focus on the semi-classical region far from the singularity, is expected to have mild time dependence. And so this you might think is not going to be too different from ADS. Okay, and if the matter is in the ground state, this is reasonable far from the singularity, you might think that the structure of this quantum extremal surface solutions that we find should be similar. And in fact, this is true. So you can show that, in fact, the quantum extremal surface now lies at the location T star and R star. So T star is the time location of the quantum extremal surface. The observer is at T0. Mild time dependence basically means that you expect T star is almost T0. In other words, delta T is small, delta T is steep, T star minus T0. And you also expect that R star goes to infinity. And the fact that we are in the semi-classical region far from the singularity means that T star is also large. This, in fact, ends up being true. You can show by an explicit study of these extremization equations that, in fact, this is true. The quantum extremal surface ends up being driven to the semi-classical region, and the entanglement wedge then, therefore, excludes the new singularity region. So this figure is, of course, exaggerated. The singularity is way over there, way in the top. And as the observer marches on, the quantum extremal surface lies here. Okay, since we are driven to the semi-classical region, the two-dimensional cosmology is a reasonable approximation to the higher dimensional cosmology. Now one can regulate the system and ask if you can get more insight, and you can in fact regulate it. So we take R star to be a finite but large boundary of the entanglement wedge effectively. And then you can show that as long as the quantum extremal surface is space-like separated, this lag is always, the quantum extremal surface always lags behind the observer. Okay, so this is the kind of picture we find. So the observer is here, the quantum extremal surface always lags behind them. You can quantify this, and you can also then show that in the presence of a regulator, the quantum extremal surface lag increases as the observer evolves in time. Okay, if you append a time-independent region far from the singularity, as just a toy example, you can this picture confirms the kind of evolution that I'm talking about here. You might ask, are there islands here? And there's a long song and dance. The bottom line turns out to be that, well, the intuition is that you might think that maybe there's something more going on here. Maybe this term flip sign, since we saw that the lag increases, you might think that maybe this term increases, and so this term might flip sign, so you don't get the sum of two positive terms. You get some non-trivial large finite R quantum extremal surface solution, and a space-like separated island-like region for this window. This turns out to not be true. It turns out. So if you analyze in detail, expanding near this island boundary, you can show that there's inconsistencies and there's no island-like solution that emerges continuously from the quantum extremal surface in the semi-classical region. So this turns out to be consistent with previous studies of closed universes with no horizons, no entanglement with elsewhere, and no flat non-gravitating Barth regions. But it's still curious that and technically interesting that this is true. So you can also show that more general two-dimensional cosmologies also exhibit very similar behavior, which then you might think begs the question of whether this is general. Is this always the way it's going to be? It turns out that that's not always the case. There are other cosmologies where something more happens, it turns out. I mean, something qualitatively different happens, it turns out. So if one looks at null Kastner singularities, so these are essentially singularities are essentially cosmologies where there's only X plus dependence. And so there's some sort of holomorphic structure that emerges. Okay. So everything here is only a function of X plus, where X plus is this combination. The dilaton here is this, and the extra scalar I was talking about is that. Since there's this holomorphic structure, you can recast the two-dimensional metric in flat variables, and that's what I've done. And now what you find is something somewhat different. Okay. So the equation of motion the equations of motion boil down to a single equation, a single non-trivial relation between between these two scalars. And so there's a whole function worth of such solutions you can find. And in particular, if one looks for a big crunch like like solution, then in fact, what you find is something like this. And you can now analyze the generalized entropy. And you can again see from the generalized entropy that in fact, there's a decoupling. You can see that there's a decoupling between the x plus and x minus sectors. This is the result of this holomorphic structure that comes out. And now you can again see that as long as you look for space-like separate, you can look for space-like separated quantum extremal surface, and it's consistent to do that. And there are in fact non-trivial solutions. What is remarkable is that the quantum extremal surface ends up lying towards the singularity. So the observers here, the singularity is over here at this slice, at this null slice. The quantum extremal surface, unlike the previous cases where it was repelled from the near singularity region, here it lies towards the singularity region. So in particular, from this relation, you can also see that in fact, x plus equal to 0 is in fact a solution when the observer x plus 0 is also 0. In other words, the entanglement wedge can potentially include the near singularity region. At least that's what this suggests. Okay. On the other hand, of course, at this level, if you analyze the on-shell generalized entropy, you can show, of course, that this appears singular generically. So you might think at this level, at the near singularity region is still best regarded as unreliable. And it's perhaps consistent with the fact that strings are known to become highly excited in the vicinity of such null singularities. But I think there's more here, and maybe one can do more by analyzing the structure in a bigger way and so on. So I'm going to stop, and I'll just leave you with these conclusions. So we saw that for the ADS-Kastner case, the classical RT-HRT surfaces anchored in the reliable semi-classical region bend away from the singularity. The quantum extremal surfaces are also driven to the semi-classical region. For null Kastner singularities, there's something qualitatively different that seems to be happening. Quantum extremal surfaces now can reach the singularity, but the on-shell generalized entropy appears nevertheless generically singular. You might ask, we've been using this reasonable intuition that we start off with ground state bulk matter far from the singularity and then extrapolate and then look for extremization within. Maybe one should be looking at appropriate non-ground state models for the bulk matter entropy. And this might then perhaps be consistent with this question about what the initial conditions are in the semi-classical region far from the singularity, and possibly non-trivial, non-generic dual CFT states. You might more broadly ask whether you might ask more broadly about which big crunch singularities are accessible via entanglement of this kind. There are further new structures that emerge when one studies de Sitter and de Sitter-like spaces. What we find is time-like separated quantum extremal surfaces generically. And this suggests that perhaps, and if you look at the classical if you look at classical extremal surface in de Sitter, it again suggests that perhaps something new is going on. So I'm going to stop here and I'll leave you with these thoughts. Thank you.
Thank you, Narayan, for an interesting talk. We have very little time for some short questions. I think Harvendra has put up his hand. Harvendra, please go ahead with your question.
Yeah. Hello.
Yeah.
You can hear me? Yeah. Okay.
Yeah.
Okay. So very nice talk, Narayan. I have a very short question. Your Kastner geometries, is there time symmetric there? Is that t going to minus t if I take?
Yeah. So everything I'm saying is on one side of the singularity. So you see, so what I'm calling t here is really is really here. I mean, so the singularity is over here. I'm going to approach everything from one side of the singularity, and so what I'm calling t here, you can think of as mod t in some ways, if you like.
Usually it is mod t, so one can actually think of something after t equal to 0 also in your case. That is my question. Yeah.
Sorry, repeat that, please. I couldn't get the last part.
No, I am saying that usually there is a mod t there in the Kastner geometry, so you can take t2 minus t and then draw the these surfaces beyond t equal to 0 also. Yeah,
but I think the physical question would be to ask how you go from one side to the other, and so that's the sense in which I'm saying that if you focus on just one side, you find that the near singularity region already looks difficult to approach.
Yeah, okay, I understand. Yeah.
Something, you have a question, please go ahead.
Yeah, Narayan, thanks for a nice talk. I can ask you this also later, but do you know of examples, let's say we reduce to 2 dimensions, like I think you were doing in some cases, where you have a classical singularity in the classical theory, you couple in matter and include the quantum back reaction, and because of the violations of some energy conditions, the singularity gets resolved in a controlled way, in a cosmological setting? Because
Yeah.
I haven't been able to find such an example.
No, I haven't either. In fact, you may remember that in that old time when we were looking at these null singularities, also we were trying to do something like that. We were trying to ask if we could find bounce-like solutions, for example. And in this model, in this two-dimensional context, also I can't seem to find that. But I don't see any reason that they cannot be. So maybe one should revisit those questions again. Is my first reaction.
Okay, well, you can actually, so what we find is you do get bouncing geometries. This is tied to what I was telling in the talk after Tadashi, but you have to go beyond the semi-classical regime of keeping gravity classical. When you quantize the full gravity theory, you can, but not in this kind of semi-classical way.
Right,
okay.
right.
Right. Okay.
That's interesting. I see.
Yeah. No, but thank you. We'll chat more. Thanks.
Narayan, I have one question.
Yeah.
So all this two-dimensional theory extern you derive from a higher dimension, possibly we assume that the higher dimension theory didn't have a dilaton. But suppose I had the higher dimension theory a dilaton, could I have found the solution where also the dilaton potential will also would have been vanished?
So in this catalog of these solutions that we had,
yeah,
one can look at, so when I'm looking for a reduction like this, I'm looking for a two-dimensional formulation. I require in some ways that this transfer space can be reduced on. Now, of course, you can relax that and do multiple reductions, so to speak. You can you can look at an anisotropic space, for example, here, and do a partial reduction on one subspace, and then do a further reduction on the other subspace, and so on and so forth. That would then lead to two-dimensional theories which are multiple scalars, which would be like the multiple warp factors for those multiple internal directions, so to speak. And presumably this sort of thing can be done then. I've just focused here on the simplest case where I look at one such.
Yeah.
I mean, one the minimal content where we have one scalar, so to speak, that comes out here, so to speak.
Oh, yeah.
Now, of course, so in particular, for example, even in this Kastner family, there's there are the generic system is a fully anisotropic Kastner system, and one of the examples, for example, has this vanishing dilaton potential. It's flat space, and it's basically the reduction of mostly isotropic Kastner.
Yeah.
But you could do what I was just saying earlier to do sequential reductions and
identification might be different. Yeah. Okay.
Yeah. So I'm not sure how much more I can do with them, but I think it might be interesting to see what you get. I don't know. I didn't have any obvious nothing to say.
Okay. Thank you very much for talk. Are there any other questions? I believe we are running short of time. There are no questions. So in that case, let's thank Narayan again. Zahed, are you